All right, so now we're going to finish up our discussion of duality, and I'll begin by drawing this picture again, where we have the sort of the two zero form or zero vector spaces, which we'll basically call the same thing, because they are the same thing. They're the set of all infinitely differentiable functions on our space-time, if we consider them as a field. And then we had the various p-form spaces, which we went all the way down to, say, an n-form. And then we had all of the p-vector spaces, which go all the way down to n vectors, right? And these ones at the bottom, by the way, we call the top spaces. So it's either top form or top vector. So it's top forms or top vectors. And then we discussed the Hodge dual, and by now we've kind of got the Hodge dual down. The Hodge dual takes n forms or p forms to 1 minus p forms, right? I suppose what I should do is I should put let me do this just so we can always have an illustration there. I'll make this n, hold on. I'll make this n minus 1. I'll erase this line, and then I'll go n like that, n minus 1, n. Well, I guess we don't need a dotted line there, right? And then we'll say the Hodge dual does this, and it does this. So it's always going from n forms or n vectors to n minus 1, it's going from p forms or p vectors to n minus p forms or p vectors. Having trouble with my colors here today. So it always goes in this direction. So we've discussed that at length now, and that's the most important one. You've got to know that one. The key about that one is simply that it depends on the existence of a metric. Your vector space has to have n dimensions, and it has to have a metric. And it's usually what we usually put the fact that it's a real vector space here, that it's n-dimensional there. And this metric here in the vector space drives a metric in the dual space, which drives a metric for every tensor product space out there. And that includes all of the exterior power spaces, right? All of these guys, and all of the exterior power vector spaces, which are these guys. So that part of the duality we've already covered. So now I want to cover the type of duality we get when we do not have available to us a inner product. That doesn't exist. Or it exists, but we're not using it for some reason. The reason is because you can establish a duality without an inner product, and that duality will move us from an exterior power space to another space of equal dimension. We already know that moving from here to here is the metric duality, right? That's the metric duality. So that's just raising and lowering indices. So although we'll probably have a quick look at that just to make sure our notation is square, that one is trivial in the sense that we already know how to do it. But moving from here to here, whoops, I guess that wouldn't be correct. It would be from here to here. Wait a minute, no, that is correct. See, it's easy to make mistakes. You're moving from P to n minus P. So that's from here to here, right? So moving from here to here, that's the duality we want to talk about now. And the Hodge duality, we'll see, is actually moving from here to here and then to here, right? That's essentially the Hodge duality. The type of duality we're about to discuss, combined with the metric duality, gives you the Hodge duality. but you always have this duality to play with too. And the reason it's kind of important is because, well, first of all, it's important because a lot of textbooks introduce duality through this concept and then introduce this duality as a secondary step, which makes perfect sense pedagogically. But many textbooks do it. Most textbooks just go straight to Hodge duality, however, because it's easy to assume the existence of a metric. It's easy to make that assumption. It's not it's not a hassle to say a metric exists, because almost always we're dealing with a metric space. So, but still, even still, you might want to introduce the concept going this way like that instead of just going straight through it. The definition, though, of Hodge duality with the presence of a metric wasn't very difficult to understand. So what about this motion? Oh, and there's another important reason. The other important reason is we're going to talk about densitized forms. And densitized forms do, in fact, begin with this movement and don't involve this at all. And those are important for understanding the different ways of visualizing these exterior powers. And we'll do my next lecture after this one on that visualization, and you have to kind of understand this to understand those visualizations. Visualizations of these things do not make things simpler to understand when you're learning it. This is an interesting fact. If you see in the comments on a lot of these lessons I do is, please explain, how do I visualize this? Or how can I intuitively understand this? And this idea of an intuitive understanding, that seems to be the favorite word. Intuitive, right? Please tell me an intuitive way, or help me visualize, which is just another way of saying intuitive, because if you can visualize it, you can generate an intuitive understanding, right? And the idea is there some quick way of getting around this stuff without mastering the absolutely abstract definition? And I want people to understand that in this material, the answer, and I'll stick by this, I'm not even going to say, in my opinion, I'm going to stick by this. The answer is no. The way to do it is the opposite. You master the abstract notion, the fact that this guy has the same number of dimensions as that guy, that these are fully anti-symmetric members of a tensor product space. You master the abstract first. And then once you have the abstract down, once you understand everything abstractly, which means you can handle the notations, you can do all of the semantic, you understand all of the notation, you understand all of the sets involved, all of the mappings, all of the rules, the semantic rules. Maybe that's the way I should say it. The semantic rules. I'm a little worried about my usage of the word semantic here, but certainly rules is appropriate. You learn all of the rules that help you understand things. And then once you have all of that down, then there is in fact a way to intuit it and to visualize it. But it really doesn't work the other way. Intuiting and visualizing it doesn't give you a handle on the abstraction. And that's really what you want. You want, if you're going to have something where you begin with the intuitive, it's supposed to be a crutch to help your mind get around the full abstraction. But in this material, it kind of doesn't work that way. It works where you have to say, you have to have gone through enough abstraction mathematics before you arrive here to not be so afraid of just bathing in this abstract idea and then mastering it, mastering the semantic rules, if that's a good way of putting it, and then, only then, do you sort of earn the right to visualize and intuit what's going on. So we're in the last phase of that. We're in the last phase of the abstraction, and then the reward for those of us who want it, and I like it, the idea, will be the lecture on this. And then I think when I finish that lecture, I'll call it quits for the what is a tensor series and move on to some other topic of particularly general relativity, or do some completion on the what is a manifold series. Okay, so let's now go back and let's understand this form of duality. Okay, so this form of duality, not depending on a metric, but it does depend on something called the volume form. Now, the volume form, I want to be careful because I'm using the word volume, and it's something that's used in the literature a lot. However, you could also think of the density form as well. The word is used a little bit interchangeably for the following object. dx1 wedge dot 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 wedge dxn. It's the top, it's the basis vector of your top form space, right? So it's the basis vector of this space. And remember, we're dealing with a coordinate system, right? This is obviously in the coordinate basis, right? We've already established the coordinate basis here, which means we have a coordinate system, x mu essentially, and we've chosen those coordinates, we've chosen an ordering of those coordinates, and that ordering is x1 through xn, and that will become our volume form. Notice this is a relatively arbitrary decision, and it's worth a little bit of thought, in the sense that if we have our coordinate system, and I haven't drawn this picture in a while, right? Say x1, x2, and then all of the rest of the xi's are out there. If we have our coordinate system and all of our space-time points, we definitely can create this basis vector for the top form basis at every point in space-time, right? We can create this guy. In fact, I can even copy and paste several versions of it, one for every point, right? It's the same basis vector in the sense that it's the same ordering of the coordinates at every point. And I can establish that basis vector for every one of the tensor product spaces, the top form one-dimensional top form tensor product spaces at every point in space-time. Now we can turn this into a top form field by putting a function of space-time in front of this whole thing. And so this particular one here, if that's the point P, will be g evaluated at P of dx1 wedge dxn. And this one, if this is the point Q, will be g of Q, of the point Q, dx1 wedge dxn. And if this is the point S, it will be, we just put a g of S up in front. And we can do that at every point in space-time. So what we've done is we've established a n-form field on our space-time S, if we call S our space-time. Right, so we've established an n-form field, and that n-form field is just g of x mu. We've already discussed fields, tensor fields, vector fields, and this is simply a tensor field called gx mu, which is essentially a scalar. There's only one dimensional. It's only one dimension, so it's a scalar function that uses this n-form basis vector to describe the field. So I'm not going to go into the subject of orientation here. I'm not going to go into that subject, but let's suffice it to say that if g of p is greater than 0 everywhere on the space-time, then our space-time is oriented. Right? Spacetimes don't have to be oriented. They're tricky when they're not. But certainly manifolds in general, or arbitrary spacetimes, don't have to be oriented. And when they're not, we have to understand how to handle all of the mathematics when they're not oriented. But we don't lose much by presuming right now that this spacetime is oriented, that GP is greater than 0 everywhere. And if we choose one particular GP being greater than 0 everywhere, we can talk about a volume form field, if that's our favorite one. But the way we almost always do that is we take g of x mu to equal 1 everywhere. It's a constant. And this object here becomes what we call the volume form. I also like to call it the density form, which is a little bit ironic because volume and density are opposites of each other. There is a reason for this. The reason has to do with how you execute integration, which actually should be the next topic once we're done with the forms. We should talk about integration on these forms. But when we integrate a form, this guy here ends up being the differentials on the integration. So we always think of that as a volume element, so we call it a volume form. However, there's another way to interpret this, and that's to interpret it as it really should be interpreted, in my view. This is a multilinear map that takes vectors, or it consumes vectors and returns real numbers. Well, you can only really integrate over the real numbers ultimately. So this thing actually consumes volume elements and gives real numbers. Well, what consumes volume elements and gives real numbers? Well, density. So I like to call this a density. I'll go into that a little bit later. I don't want to digress into the theory of integration on these forms. But the literature actually uses both. However, it uses volume form a little bit more than it uses this. However, I think this idea is a little bit more mature. The density idea is a little bit more mature. But that is actually an opinion. So anyway, once we've established a volume form, we're going to call our volume form this guy here. This better do it in black. This is the volume form, and we have to decide on a volume form in order to establish a duality of the type we're talking about. And that was true for, actually, it was also true for the Hodge duality. For the Hodge duality, we had to establish a volume form as well, remember? I'll show you how this form of duality links with the Hodge duality in a moment. So once we have a volume form, now we can start talking about the duality. Now the volume form, by the way, the dualities can go in all directions, right? So we know that we can start with this, well, let's say P, and we can go to lambda n minus P. But of course we can start with the P vector, right, and go to the n minus P form. So in some sense, we need to have two different volume forms available to us to do this. We need to define this guy, right, which we just talked about, but we also need to define this guy. Oops, let me turn off my Twitch channel. We need to define this guy, 1 to n, like that. These are both, we're going to call them both volume forms for now, right? In fact, this one I actually am happy to call a volume form. I like it as a volume form because if you go back to our lecture on determinants, we talked about how the determinant of a matrix ultimately can be understood as a volume represented by the vectors that make up the matrix as a parallelepiped. Well, these guys are vectors, right? So it's much easier to think of it in terms of a volume. And of course, this determinant is that anti-symmetry. That's sort of reflected in what this is, right? That determinant that builds this wedge product. So I like calling this one a volume form, no matter what. This one I like to give the alternative word as a density, as I was mentioning. But anyway, we got to have both of these, and I'm going to actually work from this one to tell the story of this form of duality. Okay, so we're going to call our volume form E, and we're going to write it in the following way. We're going to use the Levi-Civet assemble with two multi-indices, I and j. Now the multi-index, you remember, I is supposed to be I1 ... I, and in this case it's going to be In minus P, and j is going to be J1 to JP. So IJ is sort of a concatenated multi-index that represents I1 through In minus P, J1 JP, and there's a total of n indices. So that is what this means. This is this string of indices written in multi-index form, which is something worth getting used to. So we have to make these substitutions, these index substitutions in our mind. And that, so this volume form we're going to use is that over I1 tensor product I n minus p tensor product partial J1 tensor product partial JP, right? So this is an Einstein sum, right? This is an Einstein sum, and it is truly the this is the true tensor form of this volume element. We notice these are tensor products, not wedge products. But of course, this guy, with Einstein sums, once we make this multi-index substitution, turns it into, or is equivalent to a wedge product. There's going to be a lot of things here that are completely anti-symmetric. Those things combine together with a factor of plus or minus 1, reducing the size of this tensor product space all the way down to 1, dimensionality of 1. This is one way to write it. Then we can write it in the redundant basis as, let me erase this. If you recall the old redundant basis form, this is going to be 1 over n factorial e I j, and it will be partial I sub 1 wedge partial I sub n minus p wedge partial j1 wedge partial jp. And this this factor here corrects for the over counting of this guy, and it's still an Einstein sum. So this is still an implied Einstein sum. Okay, the reason you just saw some stuff flash on the screen is I had a recording error, so I'm now going to sort of point through stuff that I've already written. We covered up through here, now, since we set up E to be partitioned into these two parts, the first n minus p piece and then the p piece. Now we're going to introduce a p-form Q. We know it's a p-form because it's we've got the basis vector here of p-forms, and it's got a if we had a multi-index here, it would be R, right? I could in principle have made this a multi-index R, but I'm going to use R as the index for the p-form Q, and this is in the redundant basis, so you have this factor of 1 over p factorial. But if we write it in the tensor product basis, sort of like we did up here, it would just be an anti-symmetric collection of components and the tensor product of these one forms together. Just an alternative way of writing it down, and I think it's a little bit easier to understand it in that context. So we're going to kind of go with this. I'm going to omit these brackets though for now, but we know that Q is going to be an anti-symmetric collection of components. Otherwise, it wouldn't be a form at all. It would just be a regular regular 0p tensor. So what we're looking for now is we're going to look for the dual of Q with respect to E. And the dual of Q we know is going to be an n minus p vectors, because we're looking for duality in this sense, right? If this is a p form, we're looking for an n minus p vector. Of course, it works the same way the other direction, but we're looking at it from this perspective for right now. So we're kind of looking for this object, which would be the dual. Q lives in here, the dual of Q lives in here. Alternatively, Q could live here, and the dual of Q would live here. Or Q could live here, and the dual of Q would live in lambda n minus 2, or the n minus 2th exterior power of the vector space. So we're looking for this dual of Q. And what we're going to call that is the dual of Q with an asterisk out in front, which is similar to the Hodge dual symbology. So you got to be careful if you're if you're reading a textbook that's taking this form of dual, which is not the Hodge dual, they still kind of use that asterisk out in front to represent this dual. Sometimes it's superscripted, sometimes it's just in front. It kind of depends on the precision of the text editing of the textbook you're reading, whether they do it or not. And then there is this alternative notation where we're looking for the dual of Q with respect to E, and we kind of give it this symbol. And this symbol is good because it really describes what we're actually about to do. We're about to take the Q form Q and feed it to, or the P form Q, and feed it to the last P slots of the map represented by this. We're going to feed it to the last P slot. So we're going to take, and we're actually going to use it in this tensor product form. We're going to take this tensor product form of Q and feed it to the last P slots of the volume form. Now, in this case, we're interpreting the volume form as a map taking, or the volume, I shouldn't call it a volume form because, I mean, this is a vector, right? This is a n vector, this whole thing. So we're going to take this volume element, this volume object, and we're going to interpret it as a map that takes whole collection of one forms and gives real numbers. It should take n one forms and give real numbers. Well, we're going to go those last P slots and insert these one forms, these P number of one forms. And that's what this means. And this is literally us doing that, right? This is us taking Q, putting it, the R indexed Q, EIJ represents this whole thing here. It's actually just this var epsilon symbol. This 1 over p factorial is a convention. We'll talk about that in a moment. But those two are there. This is what's left over after we've stuffed these guys, or after we stuff these guys, sorry. This is what's left over after we've stuffed these guys with these guys. And the stuffing itself is right here. It's a mapping. Now, this is the one of the basis vectors of the 0p tensor product space, and this part here is one of the basis vectors of the P0 tensor product space. So this is simply a dual space mapping, just like we've always learned before, and it's going to be the delta function between this sequence and that sequence. If these two don't have the same, if R1 doesn't equal J1 and R2 doesn't equal J2 all the way through RP equaling J3, this thing will be 0. If they're all equal to each other, this thing is 1. So that allows us to get rid of this and take R and turn it into J, and that's what this expression is. Now remember, this 1 over p factorial is convention, right? Because the Q is actually coming from this version of Q, not this version of Q, right? So, and likewise, E is coming from this version of E. I've gone all the way back to the tensor product version, and that was just so I could talk about this very quickly. These are basis vectors of the tensor product space, and they're dual basis vectors, where I'm now using the word dual basis vectors in the sense of the elementary vector spaces and their dual spaces, which is a different use than the duality that we're actually dealing with now, where we're looking for a certain form of duality. This word dual gets overused, right? These are dual basis vectors, and therefore their mapping, their dual space mapping is RJ, but we're looking for the dual with respect to the volume element of Q, which is a different concept. Anyway, this is the answer, right, with this convention. And so the way we peel this answer apart is, since this is a member of the n minus p vector, exterior vector power space, I can write its component like that, and through n minus p, there are contravariant components because, of course, you're dealing with, remember, we're looking for the dual of a p form, so we're going to get an n minus p vector. The components of an n minus p vector are contravariant, they're up, they're superscripted, and it's going to equal this expression right here, where the j's are all summed out, and you're left behind with n minus p contravariant indices. And that this prefactor of 1 over p factorial is just there to ensure that if I take the dual of a p form and I get an n minus p vector, and then the dual of an n minus p vector and I get a p form, I want that answer to be very quote-unquote nice, because it's a convention. I get to sort of choose. But with this convention, the double dual, which is an n minus, or the double dual of q, which is going to be a, well, double dual is, look, this is wrong, right? The double dual of q has got to be an n minus p form. Those indices should be covariant, right? These p indices should be covariant. And so let me erase them. And R, let's see, it should go R1, RP, Q, R1, RP, like that. And we'll start our easy example with something, let's see, how about just the dual of a function, right? So imagine H is just a function on the space-time. So the dual of H, which I'm writing as the dual of H with respect to the volume form E. Remember, H is a zero. H is, we'll understand H to be a, we'll understand H to be, a member of lambda 0. So the dual of H, let's write down the formula. It's going to be 1 over 0 factorial, which is then times the volume form. And now the partitioning, this partitioning here, this partitioning to ij that we did here becomes very uninteresting. It's just all n, right? There's really no partitioning. So it's I1 ... in, like that, and H has no subscripts, and then it is simply the I1 tensor product, partial IN, like that. So that's that just really returns the volume form. So this thing ends up being H times the volume form E, where I'll try to boldface this out. So the dual of H is just H times the volume form. And that is true all the time. And in this case, it's actually kind of easy to work through the double dual just straight ahead. I said I wasn't going to do it in full generality in the last slide, but here I really don't think it's that hard. So that would be the dual of H times I1. Now here I can put it in as the wedge product, right? IN, like that, because that's what E is, right? E is this wedge product, because this is completely anti-symmetric. I'm just sort of changing up the notation just a little bit for flexibility's sake. But what is this going to be? Well, this is going to be, well, this inside, right, is going to be 1 over n factorial. So now we're doing the dual of, remember, P is now, P from the last slide here, this expression here, P is now equal to n, right? So it's 1 over n factorial, and then it's E to the, whoops, E to the, let's say, I guess it's J1, Jn, and then it's, you put that inside EI1 through IN, like that, times H, and it consumes dx1 tensor product dxn partial 1 tensor product partial n, like this. So this part here, this is now the the dual space associated with this is the original one. The guy inside here, right? The guy inside here. That's h times this thing with this vector, and we're feeding that into its complement, which is this times this vector. But there's nothing left over this time, right? What was in this formula, there's always something left over, because when you feed it, you feed this and you have this part left over. Well, now this part is simply h, right? And the 1 over n factorial is simply this p over here. So you get this guy. Well, this is just that massive delta function again, which is going to drive the i's and the j's. Actually, what I should be doing is this should be, let's see, this should be j1 to jn, and this should be I1 through IN. And this is going to create this massive delta function ij again, which is going to force these two guys to completely collapse to a real number. So it's going to end up being 1 over n factorial e, and I'll just write multi-index j, e multi-index j like that, times h. And, well, multi-index j times multi-index j, this thing, that equals n factorial. So this is going to be n factorial over n factorial times h, which equals h. So you see, if you didn't have this n factorial in the denominator, the double dual would end up as n factorial times h. So that's why that's an example of why this normalization here is so important, right? Is because we want that double dual, this double dual, to end up like this. Okay, so that's the double dual of a function. And with that, I think we've basically made our explanation, right? We've shown how you can go from a p form. Well, you can go from a p form to an n minus p vector simply by understanding a volume element. Likewise, you can go from a p vector to an n minus p form by simply understanding a volume element, right? And it's interesting because this does raise and lower indices, but it doesn't simply, a true raising of indices just goes like this, and that is our metric duality, right? And going from here to here is just like going from this and then lowering indices to get an n minus p vector, and this is again the metric duality. So another way to think about doing, so there's two steps, that's it, that's the Hodge dual, right? This 2 steps really is the Hodge dual. But another way to think about it is choosing the volume form correctly. So right now, our choice of our volume form is this epsilon I partial I1 wedge or tensor product I n, right? That's our volume form, and it's not a tensor, right? And we have no metric. We have no metric to make it. We have no metric to raise and lower indices anyway. But imagine we do have a metric, right? And if we do have a metric, we have access to the determinant of the metric and the square root of the determinant of the absolute value of the metric, and we can throw that guy in the appropriate place. Let me see. Does it go like that? No, wait a minute. It doesn't go like that. I got to get this right. It goes like this, right? Remember that from that other previous lecture. This guy here, this guy is a tensor, right? This thing here is actually a no-kidding tensor in the sense that, well, I guess I should put it, I should be a little careful, right? If I take this away, right? If I take that away, this is a tensor. It's just that when you transform it, this Levi-Civita symbol changes its values, right? But if I include this guy and put him back, then its transformation is consistent, right? It transforms exactly like a tensor, and it preserves its Levi-Civita values. And so now you can all of a sudden raise and lower indices. So here I have this sort of boldface epsilon, but now I can write this as little epsilon I partial I1 partial IN. Now this guy is a tensor. Let me just put it out in its full sense. I1 IN partial I1 tensor partial IN. I can write that out in full form, and I can raise and lower these indices in the classic sense. So if I call this the tensor, using the sort of the classic notion where I conflate a tensor with the components, I can now use G alpha I1 epsilon. Oops, I got to be careful now. I can't use var epsilons because you'll confuse it, because I want to use the components of the tensor, which will include this guy. So I want to say I1 IN, and that thing really does equal epsilon I1 I2 to IN, like that. I can actually raise and lower indices using this guy, and totally fairly, as long as I'm dealing with this true tensor. So now notice the way this is structured. If I can choose this to be my volume form, if I choose this thing to be my volume form, right, I can create this process here that I've been talking about, using, instead of E, using epsilon. And then once I get to here, once I am using that epsilon, I can actually, now that I have that epsilon, I'm not stuck with only this var epsilon with these upper indices. I can actually lower some of these guys. And then I can create a mapping, not from here, but from here to here. And that is just by modifying the epsilon. Turns out it's all equivalent. I'm just trying to make a point that this method of finding a dual with the volume form, if I use the right volume form, I can still capture the notion of Hodge duality by just lowering the indexes appropriately. So when you go out there and you're studying these different forms of duality, keep that in mind, about how well, first of all, if you're studying these forms of duality, you're almost always going to be stuck with Hodge duality, because that's the only one most textbooks talk about. But it is important to understand that it can be done just with the volume form alone, using this technique as I've described in this slide. And then once you've gotten over there, you can use the metric duality to mimic the Hodge. And then if you fully understand this notion of the tensor, the Levi-Civita tensor, then you can raise and lower these indexes earlier and still duplicate the Hodge duality. You need the metric, right? Because this guy here doesn't make any sense without a metric, because you have this determinant of the metric tensor. So it's not like you're sneaking through the Hodge duality. It's just an alternative way of defining it. Many texts define Hodge duality using this method. A lot of them do what I did, which was to create the Hodge dual for every basis vector and show you how to go about it that way. Okay, so now we have talked about several forms of duality, but we haven't talked about sort of the last one. Okay, so we're going to now try to walk carefully through this last form of duality that we're going to talk about. And I will redraw this chart with the P forms on the left. Let me just put 3 exemplars and then go down. I like this chart a lot because it sort of demystifies these spaces, because once you throw down this chart, you kind of realize there's only a finite number of these things, and you have them all under control, right? I keep putting 0 there. You have them all under control because you've drawn them all. You've written them all down. And if you can write them all down, clearly that means you totally understand them. And I'm just kidding about that, but it is a first step. Once you can get a very global picture of all the different exterior power spaces just by drawing them. And now all the questions are all the different issues are just how to map between them, right? So now, to talk about this last exterior power, or this last form of duality, I'm going to start by taking one member of the pth exterior power. So this will be a member of the pth exterior power. Now, I'm just going to talk about this for right now for this branch. This branch is the same, but we're going to define some vocabulary different. The mechanics will be identical, but the vocabulary will be different. So I'm going to work with this side just to get the one half of the vocabulary down. So we pick a member of the pth exterior power. It could be any one of these things. And then we take that guy, we take alpha, and from alpha we create alpha wedge. And alpha wedge, where wedge is your typical wedge product, that is your wedge product, and now we have a p-form over here and an open wedge over there. Now an open wedge is basically an invitation to put some form right there where you end up with a p plus q form, if this was a q form, right? And so we're now creating basically a mapping between the pth exterior power, alpha, and the p plus qth exterior power. So we're going to call that mapping alpha wedge. All right. Now, if we demand that alpha wedge only take an n minus pth form, then alpha wedge is a map from the pth exterior power space to the top exterior power space, the nth exterior power space. And I'm going to call the nth exterior power space the space of densitized scalars. So this is the space of densitized scalars. I'm going to call it scalars because the components in this are always scalars, but the fact is the top power has only one dimension. So it's got the same dimensionality as this space does. But the difference is this guy is densitized because every member would be written as, say, A, E, where E is the volume or the unit density. And as far as the vector space properties go, these might as well be scalars as far as the vector space properties of scalars go, which would be scalar addition and scalar multiplication. So these two spaces are, in fact, as vector spaces, they're isomorphic. And so this guy here is a map from oops, I wrote it as P, but that's wrong, right? It's a map from n minus P to n, right? Because it consumes n minus P forms, right? Alpha is an element of lambda P, but alpha wedge is going to be a mapping from n minus P forms to n forms. Now, literally, alpha wedge is a map from Q forms to P plus Q forms, right? But we're replacing Q with n minus P here. Replacing Q with n minus P, so we end up with maps from n minus P forms to n forms. So we're gonna think of alpha wedge in those terms for right now. We're restricting that. We're restricting this to just n minus P forms. Okay, so now with that in mind, we've now created a mapping from n minus P forms to n forms. Well, to n minus P forms to top forms. So can we create another mapping from n minus P forms? This mapping is associated with alpha in P. So once I've picked an alpha in P, I can associate with it this mapping, right? There's the association right here, that arrow. So now can I create another mapping from n minus p forms to n forms? That's not alpha p. Well, sure, because I do know that if I take an element of the dual space of n minus p, right, say I call that element omega, right, omega is an element of the dual space of n minus p, I know that omega acting on an n minus p form, that'll give me a real number, right, because that's what dual spaces are. Dual spaces are mappings of some vector space to real numbers. So that's not quite right. So a member of the dual space of the n minus p form is not going to mimic this mapping because I have to end up with a densitized scalar. So if omega is an element of the dual space of n minus p form, I know that that is this, the n minus p exterior vectors. I know that that's what that is. So I know that omega, like as I just said, I know that omega is not going to be the right map. But what about this? What about omega tensor product E? Omega tensor product E is a map from the space of n minus p forms to densitized scalars. And that's because the result of such a map is going to be omega E, that's the name of a map, right? Operating on, let's put beta as an element of the n minus pth exterior power. Operating on beta is going to be omega on beta E. And omega beta, that's an element of the real numbers, and this whole thing is an element of the top form, and the whole thing is a densitized scalar. So now I have two different maps that go from, that take us from n minus p forms to densitized scalars. Two separate maps. And so, as usual, we set them to be the same. I pick an alpha, I create a wedge, I operate on beta, and I want to get the same map as if I take some omega tensor product E, and I take that map and operate on beta. And now, for every alpha that exists in lambda p, I should be able to find an omega tensor product E that is an element of n minus p tensor product lambda n, tensor product for top form. Remember, that's an element of this. I should be able, so for every alpha here, I should be able to find an omega tensor product volume density form that's an element in this, and they should all create this. They should both create the same mapping when operating on an arbitrary element of lambda n minus p. I'll remind you that beta is an element of lambda n minus p. And in that sense, we will say that omega tensor product E is dual to alpha. Right. So that's another form of duality. Omega tensor product E is a densitized n minus p vector. And so based on this, we can say that, I'll write it down, every p form is dual to a n minus p vector densitized. right? So that is the last form of duality we're going to talk about. Every p form is dual to an n minus p vector densitized. And of course, it goes the other way around. Every p vector is dual to a n minus p, I'll call it densitized, whoops, not densitized. So that's the language change. N minus p capacitized form. Capacitized form. Because when we work on this chain here, everything's going to be the same, except everything that's in the up position goes down, and everything in the down position goes up. And this thing here, instead of being the top form, becomes sort of the top top n vector, and is partial 1 wedge partial n. And when we take a tensor product with respect to this guy, we call that a capacity. And that's because we like to think of this as the volume, which is synonymous with capacity. And we like to think of this as the density. And the density operating on the capacity gives you a real number, which is what this should be. This is a map that would take this thing and give you a real number. And we'll talk about that again when we talk about integration. But this is the last form of duality. So we have these weird dualities where p forms are dual to a densitized n minus p vector. And so now we kind of have, and this form of duality doesn't really have much of a space in contemporary studies of the subject, in general relativity or anywhere else. But a good paper to read about it is written by a man named Chris T. He never really finished the paper, but he describes this form of duality in a lot of precision. And it's important for visualization. And that's going to be our next lecture. Will be about, well, our next lecture will be about integration. I'll do them both, integration and visualization.